Good morning, students. Myself, Dr. Govind Sharma. Today we are going to start linear algebra. Now, our topic is linear transform. Before the start of linear algebra, there are some concepts we have to think about that. That first is the concept of vector space. To know about the vector space, what is the vector subspace, what is the linear combination and span of a set. So these are the activity we have to done. We have to done before there is the linear transformation. So the objective is the lecture is to know about the vector space and linear transformation, to know about the linear operator, and to understand the properties of transformation operator. So student, all the best for the new series. We are going to start. So keep focusing on that. Okay. Now I am coming to the lecture. Correct. So first we are coming to the point vector space. Vector space. This is the basic where we start the linear algebra. Vector space before internal and external binary operation. What is the meaning of? Let V be non-empty set. Okay. Let V be a non-empty set. And A is a function or mapping from V cross V to V. Then it is called internal operation because between the V we take the element from the V and get the element of V. So this is the internal mapping from V to V. So we can say this is internal operation. Now, now external operator means when F is from V to V to W. Then that means we take the element from V and V. If we take X from the V, Y from V, X into Y is equal to Z, Z from W. This is not element of Z is not element of. So this type of mapping, this type of operation we call this type of operation we call external operation. Okay. Now we come to our main topic, vector space. What is that vector space? Vector space. So this is the definition of vector space. An algebraic structure algebraic structure V plus Vihar plus is internal Binary operation is a vector space or linear space. This can be linear space also on a field F on a field F plus dot if it follows some property. Some property. An algebraic structure with B plus, where plus is the internal binary operation. By internal binary operation means B cross B is come the element from V. It gives the element of C. The binary operation is a vector space or linear space on a field F plus if it follows some properties. Number one, B plus, you can take it this type, B an abelian group. B plus is a abelian group. That means abelian group we have already discussed in abelian group in abstract algebra. Okay. In abstract algebra we did the abelian group if G plus is an abelian group, that means G plus is a closed, G plus is follow the associative property, G plus is a have the identity element, and G plus is a have an inversion. So, and also for abelian, G plus follow the commutative law. So this abelian group concept from you can understand by abstract algebra series. We have very deeply I have discussed on group. Okay, group I like here. G plus is a group if first closed, second associative, third identity element, fourth inverse, and fifth commutative. So this is the first property when a algebraic structure shows this is called the abelian group. Now come to our second condition for vector space. Alpha belongs to F. F is a field. V belongs to V. That means alpha dot means multiplication. This is called the scalar multiplication also from where alpha belongs to third scalar multiplication distribution. That means alpha dot V1 plus V2 is equal to alpha dot V1 plus alpha dot. This is the distribution property. Third is force property means associative force for scalar. Force. Associative for scalar product means alpha and alpha to two element of F and V1 belongs to V, that alpha 1 dot alpha 2 dot V1 is equal to alpha 1 dot alpha 2 dot fifth is 1 dot V1 belongs to we have 1 belongs to F is identity. Okay, so student, a vector space is an abelian group. Okay, this is fine. Alpha belongs to F, F dot V belongs to V. Okay. Third, scalar multiplication distribution V1 plus V2 distribute by alpha, an associative property for multiplication, and multiplication identity element is also exist. So this, if a algebraic structure fulfill this condition, then algebraic structure fulfill these conditions, then we say that this is a vector space. Okay. Now, if we take remark, if we take field at f is equal to r, then field f is equal to then v plus is said real vector space. Real vector space. If f is equal to q, then rational vector space. Third, f is equal to c, then complex vector. So these are the vector space according to the field we can describe. Okay. Now a set of real number R is a field. It is also vector space of it. These are the some remarks like R, a set of real number R. A set of real number R is also well vector space on itself. Also vector space on itself. That means that means R you can like this. Okay. A set of real number R of a field is a field. Then it is also vector space on. Second, complex number set C is also on-field vector space. Set of polynomial is also a set of polynomial is also a the set of polynomials is also a vector space. Okay, set of polynomial is also vector space. So here we discussed friends three types of R, C and set of polynomial is already. So here we see again vector space means an algebraic structure V plus is called vector space. It's called vector space for an internal binary operation. Binary operation I have already told that it is closed. So V plus is in abelian group. Alpha belongs to F, V belongs to A. Alpha V belongs to V. Alpha dot V1 plus V2 is this. Follow the distribution law. Associative property of scalar product and distribution property for a multiplication and identity element. Identity element. So these are the now F if अगर we take field is equal to R then it's called the real vector space. If if F is equal to Q then rational vector space and then F is equal to Q complex. Okay. Now here are some example of vector space. Okay, students. Now the set of polynomial. Polynomial means we know the set of polynomial is Px is equal to a0 plus a1 x plus a2 x square a cube x cube. This type of set is also a vector space where these are rational integer. ठीक है? A1, A0, A2 are the constant. Okay. Now we take some example of vector space. We will have to prove some theorem which are very important with respect to the exam and competitive exam. Theorem first. Prove that a field F is a vector space over any subfield S of. That means we want to say that a field F is a vector space over any subfield S of. Let F plus dot F plus dot be a field and S be a with subfield of F. Let F be a कोई field है and S be a subfield has a subfield S. That means has a subfield of or F. So all elements of S from F and each scalar product for all alpha belongs to F and for all alpha dot belongs to. That means alpha dot B also belongs to. Now we will show so Fn is linear. Abelian group for first we show abelian. For abelian group, F plus is a field we know that and given also that F plus dot is a field. So F plus dot be an absolutely abelian group. Student, in abstract algebra, we already know that a field is also a commutative ring with unity for integral domain. And integral domain is also a field is also a ring, and ring has the property of F plus is a abelian group. So F plus dot is a field, so we can say that F plus is always be abelian group. So F plus B. Now we take on SB is the subfield of F plus dot. So S plus is also abelian because given that S is a subfield, then it follows the all property of abelian group. Second, distribution on multiplication. Let alpha belongs to S. That means alpha V1 plus V2 is equal to alpha V1 plus, okay, because F is a field, so alpha V belongs. Now third, distribution on scalar addition. Distribution of scalar addition. Let alpha 1 alpha 2 belongs to S and V belongs to S. Then alpha 1 plus alpha 2 dot V implies alpha 1 dot V plus alpha 2 dot V because as here we can see that alpha belongs to S, V belongs to S, so alpha V also belongs to because F is a field. F is a field. So we can say that is follow the this term we can write like this. So this follow the distribution on scale. For for associative. Associative means let alpha 1 alpha 2 belongs to that and V belongs to. Now F so alpha 1 dot alpha 2 also belongs because F plus dot is we know we know a field always follow associative now the last one is because F is a field so it has the multiple identity multiplication identity so we can say that one belongs to F one belongs to S is a field of so one dot B okay okay because one is the identity for multiplication so we can say that one is the F is also field so one is a part of So we can say 1 dot v. V from the element of F. So we, 1 is the identity element, so 1 dot v डालने V and V belongs to F. So 1 is identity element. By above, we see that F plus dot satisfied all the conditions of a vector. So we can say the field Fs is a vector space. Okay. Now again we move to the second theorem. Prove that we can write and write that prove that the matrix set is 0, 0, 0. AB belongs to R. Is a vector space over the field R of real number occurring with respect to matrix addition and multiplication. So friends, we have to show first some points on matrix. We take some points, prove. First we have to show let V. First we have to show that V be a closed for addition and multiplication. For addition, we take two elements from V, and V1 and V2 are two elements of V. And which type of element it has? It has the 2 by 2 matrix. V2 is equal to A2 0 0 V. This type of element, diagonal element, it has. Okay, so then we keep then V1 plus V2. We find out the value of V1 plus V2. A1 0 0 V1 plus A2 0 0 V2 is equal to A1 plus A2 0 0 V1 plus V2. Because A1 is belongs to V, A2 is belongs to V. So, and real number, sorry, this is a real number. Real number. So A1 plus A2 is also a real number because the sum of two real numbers is always real number. So this is, and similarly B1 plus B2 is also real number, and we have the element where A and B are the real number. So B1 plus B2, we can give the name C1000C2 is also element of, okay, also an element of 6. Then we can say, then we can say it is closed. It is closed for addition. Now, now we take any scalar alpha, alpha from to f and v from to v. Alpha we take out and b is equal to a 0 0. So we know that a belongs to R, alpha is any element. Then a, the scalar product with R. If any element from the R and any from, we when we dot product with a R element, then the resultant is also from the R. So we get alpha is 0 0. Now we know alpha belongs to R. So this is also belongs to, this is also belongs to. So we can say alpha belongs to F, V belongs to V. Then alpha V also belongs to this is our. Now, now we move to our target. Now we move to our target. First, we will show that this is an abelian group. Now, first we have to show V plus is an abelian group. So we see that closed property we have already shown. Now we take three elements V1, V2, V3, and we know that the addition is always associative property. So the addition of these addition operation always show associative property. Now second, identity element. What is the identity element? The zero is belongs to real number. So we can say that 0 0 0 0. If we take A is equal to 0 and B is equal to 0, then the matrix convert in 0 0 0 0 plus A B 0 0. So we get A plus 0 0 0 B plus 0 belongs to, and belongs to R means belongs to V. So we get, because we this type of element having V. So by this element addition operation with this, again we get same V. So this 0 0 belongs to V is identity. Similarly, if A B 0 0 belongs to V, then implies minus A, because minus is also element of real number. It also belongs to V, and the product and the addition of these give us the identity element 0, 0, 0. That means that means minus a 0, 0 minus 0 is inverse. Okay. Now student, we have to show commutative because addition is always commutative follow the commutative property. So this is okay. Now this is remaining. This is home assignment for you that scalar product associative property and multiple identity. You have to show that remaining part of this is satisfied and the set of matrix. This type of matrix each and is a vector space. Okay. So now we move for the queues. Now we discuss on the queues. Which is a vector space, student. So in this lecture we think about the vector space more deeply because which fulfills the some condition, then we say that this is a vector space. But n plus is exactly definitely not a vector space. And R plus, I already told you that R is a vector space on itself. So R plus is a vector space. Which is the LT? LT means linear transformation. So this is the we will continue. Okay, when we come to the linear transform, we will discuss a linear operator mapping from closed associative, actually closed associative identity element. This is the part of vector space, but the mapping is always on itself. It's called linear operator. Okay. What is the linear transform? A linear transform means which of the linear transform is Px is equal to M. So student, I hope the vector space in clear in your mind. You make an image of vector space, which type of sets, which type of algebraic structure we can say vector space, and what is the field. So now we will continue with this topic and further lectures. We will discuss with the subspace. We will come to the linear combination and dependent dependent variable vectors and independent vector, and then we move from the linear transformation and then matrix. This is a long continuous process, so keep continue with me. Thank you very much.